Where's the IT man when you need them? Okay. Final talk of the day before we do the closing slides and then go into our pizzas and drinks. I'll get on the right page. It is again Surinder Sood of ARM, who's a principal engineer at ARM. He's going to talk about a novel security vulnerability detection mechanism using information flow tracking on a given SOC. He's a principal engineer, a visiting researcher at the University of Manchester, and is a senior member of the IEEE Circuit and Systems Society. Okay, thank you, Surinder.
Yeah, thanks, Mike. So hi, everyone. I'm sorry I'm back again. So now I'll be talking on a technique which we developed to detect the security vulnerabilities on a given system. So this solution has been tested on various client SOCs while I was working for Intel. So I will start with first of all, different kind of access mechanisms in a given system and the motivation behind developing this solution, and a brief overview of what's information flow theory, what's my proposed solution, and evidence, and then conclusion. So the terminologies are to be discussed must be, I think, known to everyone. NCA stands for non-coherent access. NCP is the non-coherent path. Security class is a set of access rights for a given resource. Equivalents of security classes, which are also called trust boundaries. So the classes which have the similar access rights, and the trust boundary, which is the set of objects which belong to the equivalent security classes. And FM stands for the information flow model. So the background of the solution is this. So if you see any system, typically system on chip, so you have two kinds of paths. One is a coherent path and other is a non-coherent path. The coherent path basically deals with the kind of data which starts from CPU and ends to memory and vice versa, right? So it spawns over an interconnect, and the duty of the interconnect is to direct the traffic to the relevant memory destination. It also has on its path various CPU caches, L1 cache, L2 cache, and stuff like that, and a common L3 cache depending on the architecture. On the contrary, we have another path, which we call as a non-coherent path, which caters to various configuration stuff like configuring various nodes, configuring registers, configuring some functionality and stuff like that. Secondly, it also deals with the data which spawns across peripherals, MMIOs, IO devices, but not caches. Now, here the focus is on the non-coherent access. So when we do any non-coherent transactions, so the guys who are in perspective are software agents like BIOS, applications, application software, drivers, etc., or hardware agents like CPU. And whenever any agent wants to access a specific memory area or any register or stuff like that, so so it has it can only be allowed access to a specific register, for instance, if he has the permission to access that. Otherwise, it is not given any access. If we think of SOC, a given SOC has thousands of such registers, so which are requested by many agents. Many examples are given here. And on top of that, one register as a source can be accessed by multiple agents. And any agent can be given access to a given register if he has the permission to access that. Now, access can be read access can be write access, or access can be read write or stuff like that. Now, when we do SOC verification, the existing solution is shown in this slide. So we define the register definition for all such registers which are accessible by all the agents over non-coherent paths. So what we do, we have the RDL model for such registers, which we define as register definition language. And then from the RDL, we extract certain access permissions. And to test whether your design is adhering to those permissions when such requests are made, So we write hundreds of tests, not hundreds, sometimes thousands of tests. And everyone knows that when we run one test in a given system, it takes more than 2 hours, more than 3 hours, or sometimes more than 10 hours, depending upon the complexity of the chip. So this means that the existing solution is complex, time consuming, and compute intensive because it utilizes a lot of compute power. And finally, when we do the manual coverage analysis of such register accesses, and I think it's a hell lot of a job. So in order to elevate all these things, we came up with a solution. So what we do is, so the methodology is shown in this figure. In the first step, we have the register definition language. So what we do, we extract that RDL, meaning the RDL information for all the registers. And then what we do, we model all the access permissions using a technique which is called information flow tracking technique, in which we mathematically model all the access permissions of all the registers which are accessible by all the agents in a given system. Now, in this case, when I speak of a system, so it's not just a hardware thing. It is a firmware, it is an application, it is a driver, and it can be obviously CPU or any hardware agents as well. Now, using the IFT-based technique, we model all those access permissions, all those access paths. And then once I have the definition, the mathematical definition of all those accesses, we spawn a threat report, meaning we on the fly create all the properties, which are typically system verilog assertions, or it can be PSL or whatever the choice. So we spawn all the properties which are actually checking the negative part, meaning it is always checking where the access is not allowed. We can also generate the safety properties also, or the positive checks also. But here the scope is security vulnerability verification. So we generate all the negative properties of it, out of it. And simultaneously, as a next step, we also create stimulus for that. So that is the step 4, which says scenario generation. Now, once we unroll all the properties and once we create all the stimulus, which is readily created, because it's just a kind of a automated program which unrolls on its own after parsing all the RDL definitions of all the registers in a given system. So we execute those tests, and then we generate the coverage report. And if it is a miss, we repeat the loop again. And if it is a hit, this means that we have checked the relevant scenario. So this is the proposed solution in brief. Now, what is information flow tracking? Information flow tracking, basically, it's a mathematical technique using which we can represent the information and data which is flowing across a given system. So for more details, you can refer to the paper which we published some couple of years back. So basically, it verifies whether the data movement between a given source and a given destination is allowed or not allowed. And an information flow model, which we call as FM, it is specified on a DUT to DUT basis. So we can give an example in this case. For example, let's say you have two objects like A and B. And these two objects want to write to some destination, which is C. Now, A and B can write to C if A is allowed to access C and B is also allowed to access C, regardless of the fact whether they have different access permissions or same access permissions. If they have different access permissions, then this means that there will be an intersection of the permissions such that both the sources can write to the C. So A and B are ABC are the objects, and using the information flow theory model, so we actually check this, and once this is checked, and trust boundary is established between A, B, and C. Now within that trust boundary, you can do as many operations as you want. So this is what is defined using the information flow model. So for a given register in SOC, so if we figure out all the non-coherent paths, and we generate all the non-coherent accesses, like the one as I gave an example, A is equal to B plus C or something. So we generate all the non-coherent accesses from the NCP. And the security of any register is equal to the control security, access control security of the register. And that NC is secure if and only if all the paths, like in my example ABC, if all the paths, like the path between the target, which is C is equal to A plus B, the path from A to C and path from B to C, if it can be established, then that trust boundary is said to be established. So using that mathematical technique, we unroll all the trust boundaries, dump properties out of it, and then we do the verification. So for example, in this case, if it is a typical SOC where we have one bus and one core, for instance, and one bus actually then connects to different targets like peripheral, security engine, or the memory subsystem. Now, NCP is a path for the data to reach these storage objects, like the dotted line shows the NCP paths which can be established. And then the storage objects in this case are the registers. So when we run this, when we run our technique on a given SOC, so this is the evidence for that. So we had, tens of thousands of non-coherent accesses. And to execute those non-coherent accesses, we have 20,000 plus non-coherent paths. Now, in order to check that, if we do with the conventional approach, so it will not be possible. And what we do in the industry is actually we just take the important things and we verify, and then we say, oh yeah, it's kind of working. Because to test all such paths using standard SOC simulation or emulation technique, that's not possible. And in our case, when we generated tests and when we generated properties, so it was kind of like we just devoted 150 minutes of test per 10,000 threat scenarios. And number of IPs and components, we explored like 4 hardware agents and 3 software agents. And it was a 3 weeks development work. And the kind of properties we unrolled or unearthed, so they were seamlessly usable at different levels, that is simulation, emulation, and post-silicon. And using this technique, we found 5 bugs, which were kind of on the products, which were derivative products. And in the previous episodes of verification of the same product, so those bugs were not detected because of the limitations in the stimulus. So this is what I had in brief. So I'm open to questions.
Yeah, thank you, Sundar. We are open to questions for only questions. Otherwise, we will be finishing a little bit early, which isn't too bad. It allows us to set up for the final session. Any question for Surinder? Yeah. We have one question, yeah. Perfect. Thank you, Surinder.
Thanks. I was wondering about the corner cases that you didn't catch before that your flow was able to catch. What kind of corner case was that?
Yeah, that's a good question. So, as from Intel x86 architecture, so any access permissions which are given to registers, they are defined in their SI policies. So SI policies are called security access identifiers. Every register has a specific SI policy for a given agent, right? So this means that if you have multiple agents who are accessing a specific register, so he will be accessing under different SI policies. Now, so this kind of scenario exists in case when we are, doing various configuration of a given SOC. For example, you want to have some specific FIFO memory depth or buffer depth in a given interconnect, or I want to play with the cache size for a given requester in a given configuration. I want to alter the different clock frequencies, right? So when we do all these things, so in a specific configuration, the SI policies are programmed accordingly. So the corner case bugs were found in case when you were playing with the memory depths at different levels and in a given security privilege level. So these things were missing in the stimulus in the previous versions of the verification of the same client SOC. But when we implemented this, so these kind of things were unearthed.
More. Okay, thank you to Surinder.
Yeah, thanks.